Now that we've learned about ionic bonding, I want to introduce you to another way that atoms can satisfy the octet rule, namely through the formation of covalent bonds. Our learning goals for this video will be to understand the nature of covalent bonds and how they lead to a certain covalent bonding capacity for each element, and then we'll draw a distinction between molecules and ionic compounds. So there's a second way that atoms can satisfy the octet rule besides just gaining or losing electrons. They can share electrons with other atoms. So you might think of this as a more friendly way of achieving the octet rule. Let's consider two hydrogen atoms. Now here's a cartoon that sort of shows you what might happen when two hydrogen atoms come together. Now the nucleus in these atoms is drawn way too large. It's normally much smaller than that, but it's drawn there so I can fit a +1 in the middle of it. Now each hydrogen atom has a single electron. Those electrons not only feel the attractive force to their own nucleus, but they also feel an attractive force from the other nucleus, because in general they cannot shield each other very efficiently from the other nucleus. So the net effect is these two atoms are attracted toward one another. As they come together, those two electrons become shared between those two nuclei. And even though the electrons are repulsive, and as are the two nuclei of the two atoms, there's nevertheless a net attractive force that holds them together. Those electrons become shared, and so we see in the lower right a new sort of Lewis dot diagram where we've got the two hydrogen atoms with two electrons that are in between them and in some sense sitting in the same quadrant. Okay, those represent the covalent bond that is formed between the hydrogen atoms. Now another way that we write this more commonly is rather than draw the two dots for the electrons, for each pair of electrons that are forming a covalent bond, we draw a horizontal line that connects the two elemental symbols that are forming the covalent bond. So the whole idea is that the two shared electrons equals the covalent bond. Now, we're talking about diatomic molecules here, which is a molecule that has two atoms held together. A molecule itself is a group of atoms held together by covalent bonds. When there are only two of them, then it's a diatomic molecule. An example that we've already seen is H2, but let's also look at another example. F2 can also come together. It has one vacancy in its valence shell, so it can come together with another fluorine atom, and each of them takes the one lone electron they have not paired with another in the valence shell and slot it together, and the two of them can together form a covalent bond. So each valence shell now contains an octet of electrons. We can draw circles like this, and you can see those two circles overlap, and the electrons that are in the overlapping region in the middle are the ones that are forming the covalent bond. So we would also draw this using that horizontal line to represent the covalent bond. Note that each of the fluorines also has non-bonding pairs of electrons. We'll see that on a number of atoms. Fluorine, nitrogen, oxygen all have non-bonding electrons, and when they form bonds, they typically have some extra electrons out there that are not part of the bond. So let's make a distinction. This is going to be an important distinction because it's often confused by people who are coming new to chemistry, and that is the difference between molecules and compounds. Molecules are groups of atoms held together by covalent bonds. They have to be covalently bonded in order to be a molecule. They tend to be standalone entities. In other words, you can have a single molecule and it's perfectly stable in outer space. They may consist of several atoms of a single element or contain atoms of different elements. In other words, you can have mixtures of atoms, or you can have all of them be the same atom. Okay? It can be homogeneous or heterogeneous mixtures of atoms. As long as they are all covalently bonded together, they form a molecule. Compounds, on the other hand, strictly refers to a substance that has more than one element. All right, so that can be a covalent compound, but it also can be an ionic compound. Most ionic substances are compounds. All right, so they are automatically compounds. We can have covalent molecules that are not compounds if they all contain the same, if all the atoms are the same element, like we've seen with H2 and F2 before. Now let's learn something about the bonding capacity of each element. That is basically the number of covalent bonds an element can make. Okay, now we can find out what that bonding capacity is by looking at its Lewis dot symbol, thus the reason for learning how to draw those, and determine how many single unpaired electrons there are. When we know that number, that is the number of bonds that element can make. That is, in effect, its bonding capacity. So here are several of the elements in the second row of the periodic table, going across boron, carbon, nitrogen, oxygen, fluorine, and neon. And what we want to do is evaluate these Lewis symbols to determine what their bonding capacity is. Now note that the full circles on each of these are electrons, and the open circles represent vacancies in the valence shell. So now let's determine what the bonding capacity would be for each of these. In boron, we can see that there are 3 vacancies next to 3 electrons, so it has 3 unpaired electrons in its valence shell, so it has a bonding capacity of 3. In carbon, I think it's pretty clear, it's got 4 electrons and 4 vacancies, so with 4 unpaired electrons, it has a bonding capacity of 4. Now we need to be a little careful when we get to nitrogen, because it has a pair of non-bonding electrons on the left-hand side. It has 3 unpaired electrons along with 3 vacancies, so it has a bonding capacity of 3. It can only make 3 more bonds. Oxygen, similar to nitrogen, has has pairs of electrons that can't form bonds, but has 2 unpaired electrons that can, so it has a bonding capacity of 2. Fluorine, as we've already seen, can make 1 bond, and then it has a filled valence shell. And neon has no vacancies at all and no unpaired electrons, so its bonding capacity is 0. Now you get to try a few. I want you to predict the bonding capacity of selenium, arsenic, and bromine from the Lewis symbols that are shown here. I'll give you a second. You can pause the video. All right, what did you get? For selenium, you should have gotten 2. It has 2 unpaired electrons on either side. For arsenic, you should have gotten 3. It has 3 unpaired electrons. Bromine is like fluorine. It has only 1. So these are the bonding capacities you should expect to find for these elements. There are trends in bonding capacity just as there are trends in the ions that are formed. Okay, so we can see those trends when we fill out the bonding capacities on a chart like this. Okay, note that I'm only going to talk about nonmetals. Metals do form covalent bonds with themselves and with other metals, but mostly they form ionic compounds. In the case of the nonmetals, though, we do get lots of covalent bonds. Already we know that the noble gases do not form bonds, so their bonding capacity is 0. For hydrogen, it's a bonding capacity of 1. Now we're going to skip over the second column. When we get to the third column, there's a bonding capacity of 3. When we go over to fluorine, that also has a bonding capacity of 1, as do all the halogens below fluorine in that column. Oxygen and its group partners, sulfur and selenium, have bonding capacity of 2. Nitrogen and phosphorus have bonding capacity 3. And carbon and silicon have the largest bonding capacity, at least on this chart, of 4. So this gives you an idea of what kinds of bonding capacities we can find and what kinds of molecules these are going to make, because this tells you how many bonds each of these elements makes.